Hello, my name is Muhammad Firdaus and I am the group leader for chemistry assignment ES4 group 10. And today, our group will present our chosen energy bearing compound that will be used in our case study 1. But before that, I would like to introduce our members.
Hi everyone, my name is Wan Nazif and I'm the video producer.
Hi, I'm Nurul Aminah Zahira and I'll be making a poster about this topic.
I am Nabil. I will introduce you to our scenario of the case study.
My name is Sakura and I will explain our problem statement and the proposed solution.
And I am Haras. I will conclude all our findings.
Okay, I'm back. My role is as the leader and the one analyzing the data. Phew, such a heavy job. But anyway, let's get to know our case study.
Well, here's the deal. Energy Storage System ESS, owned by Evercam, plan to use the usage of octane to store energy suggested by their engineers. But the process of producing octane from carbon dioxide has been used by other companies. So, our job would be finding another compound to replace octane. The target is to convert the energy from power plants and store it as chemical energy to transport it to the city, as it can generate electricity for residential and industrial usage. As such, in this case, we will be using the first law of thermodynamics, which is energy cannot be destroyed and created, but can be converted from one form to another.
What compound would be suitable to replace octane to store the energy? That would be the problem statement for our case study. Meanwhile, the objective of this case study is to determine a suitable compound to substitute octane and come out with a new unit process at ESS plant. So, let's get to the proposed solution. Our chosen compound is nonane. Here are some of the justification. In the graph shown, nonane has a higher energy density, which is 34086 megajoule per meter cube, compared to the octane, which is 33433 megajoule per meter cube. It contains more carbon and hydrogen atoms per molecule, resulting in a higher energy content per unit volume. This can provide a greater energy storage capacity and potentially longer operating times for the ESS plant. Nonane can release a significant amount of energy when combusted, making it suitable for power generation. The specific energy of nonane is approximately 44 megajoules per kilogram, while octane has a specific energy of around 43 megajoule per kilogram, as shown in the graph.
Moving on to the unit process. Firstly, solar energy is harnessed using photovoltaic systems or concentrated solar power plants to generate electricity. Next, the generated solar electricity can be utilized to power high-temperature thermal processes required for fuel production. Thus, concentrated solar energy is used to drive high-temperature reactions such as steam reforming or solar gasification to convert carbon sources such as biomass into syngas, which is a mixture of carbon monoxide and hydrogen. To produce syngas is further processed through catalytic reactions such as Fischer-Tropsch synthesis to convert it into liquid hydrocarbon fuels, including nonane. The resulting liquid hydrocarbon mixture is refined and processed to isolate nonane and remove impurities. Lastly, nonane fuel can be stored in appropriate storage systems such as pressurized tanks or other suitable container. as a gas.
Okay, since we already have the chosen compound, there are some data we need to deal with regarding to the related chemical reaction. First, let's evaluate the factors that affect the rate of reaction. The first factor to consider is the physical state of the reaction. In a homogeneous reaction, carbon dioxide and hydrogen are in the same phase, making the reactant readily collide with one another. Thus, it reacts more rapidly and the rate of reaction increases. Next is concentration. As the concentration of CO2 increases, so the frequency of collisions increases. The frequency of effective collisions also increases. Therefore, the rate of reaction increases. Besides that, the temperature is also one of the factors. When the temperature of CO2 and hydrogen increases, the kinetic energy also increases, thus increasing energetic collisions, and then the rate of reaction increase. And lastly, the factor affecting the rate of reaction is catalyst. In this chemical reaction, ruthenium catalyst is used. It acts as a surface for CO2 and hydrogen to bind. Therefore, the activation energy will reduce, causing an increase of rate of reaction. Now, let's determine the standard heat of reaction and the entropy change for our selected reactions and analyze the Gibbs free energy equation to predict the effect of temperature towards the reaction. The chemical equation for synthesis of nonane is shown, and the following table shows values for standard heat of formation and standard molar entropies for each substance in the chemical reaction. From the given values, the calculated standard heat of reaction is negative 1876.79 kJ, while the entropy change is negative 3930.68 joule per Kelvin. Moving on to the Gibbs free energy, as the reaction are exothermic, the delta H is negative, and since the reaction produces liquid from gas, the delta S is negative while T is positive. From the formula of Gibbs free energy and the table shown, we can see that the reaction is non-spontaneous at high temperature but spontaneous at low temperature. To get a spontaneous reaction, the temperature must be less than 477.5 Kelvin or 204.5 degrees Celsius as shown in the calculation. However, there are limitations for this reaction. The reaction is not favorable in low temperature due to collisions not energetic enough. But for thermodynamic limitations, it depends on spontaneity of the reaction, which is in low temperature. So, to overcome it, we can increase the concentrations of a reactants and use catalyst in this reaction.
To sum up, we choose nonane as the energy-bearing compound due to its various properties. The unit process has already been determined and explained. Nonane has high specific energy capable of releasing substantial amounts of energy. With its high energy density, it is also capable of storing high energy content. A high spontaneity for the combustion reaction of nonane as calculated implies that it occurs readily and efficiently, allowing for the rapid combustion of nonane. This can be beneficial in terms of energy production and minimizing the release of harmful byproducts. As nonane is formed from carbon dioxide, the goal to maintain carbon neutrality can be accomplished. As such, all objectives are achieved.